Hello, this is my fourth class for numerical analysis for fifth year student of Kolhan University, a fifth semester student of Kolhan University. I am Ms. RANJANA Dutta from the Department of Mathematics of Graduate School College for Women. Now, last day we studied about the Newton's forward formula and Newton's backward formula. Now, today I am discussing the numerical differentiation applied on Newton's forward formula and Newton's backward formula. As we know from the last class, Newton's forward formula, that is y is equal to y0 plus u into delta y0 plus u into u minus 1 by factorial 2 delta square y0 plus u into u minus 1 into u minus 2 by factorial 3 delta cube y0 and so on, where the function y is equal to fx for every x, and x is equal to x0 plus ih. Differentiating both sides with respect to x, that is differentiating the Newton's forward formula. dy by du, when we differentiate with u, we can write it as y0. When differentiated, it becomes 0. Then u into delta y0 means u, differentiation of u with u is equal to 1. Similarly, differentiation of u into u minus 1 by factorial 2 is 2u minus 1 by factorial 2 and delta square y0. Next, u into u minus 1 into u minus 2 when differentiated with respect to u gives 3u square minus 6u plus 2 and factorial 3 and so on. Now, but x is equal to x0 plus nh or uh, where u is equal to x minus x0 divided by h, where x0 is the first value of the variable and h is the interval and x is equal to the value we have to calculate. Now, du by dx, from this we can see that du by dx is equal to 1 by h. Now, dy, we have to find dy by dx, and which can be written as dy by du into du by dx. And as we know that du by dx is equal to 1 by h, and dy by du we have calculated before, and that is written, that should be right here. Next, x is equal to, when x is equal to x0, u is equal to 0. When x is equal to x0, u is equal to 0. That case, dy by dx, in dy by dx, put x is equal to 0 and whatever with the value comes, that is on your screen. For further, differentiate 1 with respect to x again. Differentiating the equation 1 with x again, and that can be written as d of du within bracket dy by du into du by dx. We have calculated dy by du earlier, and from that we get del 2y by del x dx square is equal to 1 by h, 2 by factorial 2 del square y0, and further written. Now again put u is equal to 0 in the table and we get the whatever comes in the screen you can see. So del 2u by del, similarly del 2u, del 3u by del x cube is equal to 1 by h cube and del cube by 0 as seen. No? Now, for the backward differences, we know y is equal to yn plus u nebula yn plus u into u plus 1 by factorial 2 nebula square yn plus u into u plus 1 u plus 2 by factorial 3 nebula square yn and so on. This can be also written as fx is equal to fx plus nh plus u nebula f x plus nh plus u into u plus 1 by factorial 2 nebula square fx plus nh and so on. As we know, delta table and delta table and nebula table are the same, but uh, but we call when we subtract we subtract the first value from the second value, we call it as delta of first value and nebula of the second value. Here, dy by dx, backward formula is written, and dy by dx, that is differentiating with respect to u, we get delta of y0 plus 2u plus 1 y factorial 2 delta nebula square yn and 3u square plus 6u plus 2 by factorial 3 nebula cube yn and so on. Yn is the last value of the variable. Here u is equal to x minus xn, that is xn is the last value divided by h, and this implies du by dx is equal to 1 by h. So dy by dx is equal to dy by du into du by dx. So this becomes 1 by h for dy by du by dx, and the remaining factor written in brackets. So at when x is equal to xn, that is last value, u is equal to 0. And when we put in dy by dx, x is equal to xn and u equal to 0, we get the value written on your screen. Similarly, d2u by dx square can be written as ddu dy by dx du by dx, and that is equal to 1 by h into within bracket the variable written. Thus, putting u equal to 0, we get d2y by dx square. This is second derivative. d2y by dx square is called the second derivative, and dy by dx is called the first derivative of the function. Now, take two examples of finding the first derivative and second derivative of Newton's forward formula and for Newton's backward formula, as shown on your screen. Now, Newton's Gregory formula, we know Fa plus Xh is equal to Fa plus Xe1 delta Fa plus Xe2 delta square Fa and so on. Xe1 means x, Xe2 means x into x minus 1 by factorial 2, Xe3 is equal to x into x minus 1 into x minus 2 by factorial 3 and so on. Now, differentiating this, we can write it as, with respect to x, we can write it as h into f dash a plus xh is equal to delta fa plus 2x minus 1 by 2 delta square fa plus 3x square minus 6x plus 2 by 6 into delta cube fa and so on. Mind it, in forward formula, A is the first value of the variable and fa is the corresponding function. Similarly, h square, again differentiating this function, we can get h square f dash a plus xh is equal to delta square fa plus x minus 1 into delta cube fa and so on. Now, we are to find the value of f dash 1.1. For this, x is equal to half. And we know h is here equal to zero point 0.2. So we take h is equal to 0.2. So seeing the from the table we can find the value of this, and which comes to 0.264. So f double dash 1.1, that means again differentiating the function and substituting the values from the table, we get f double dash 1.1 is equal to 6.60. Hence, we know also that if the functions are not given and y is in the form x cubed minus 3x plus 2, so that dy by dx is 3x square minus 3 and d2y by dx square is equal to 6x. Now, take another example of Newton's backward formula, and that is find the value of find the derivative of fx at x equal to 1.4 from the given table. So you prepare a difference table and using backward formula that is written, you know all, and that is written, then substituting the values of these on the formula, and we can get the value of f dash x, that is the first derivative, and f double dash x in the that is the second derivative. You try at home. This is your homework. Okay, bye. Thank you.